Thank you. As you said, I'm Rick Reed. I'm from a small startup you've probably never heard of. I want to start by apologizing for the title. When I submitted the talk in December, I did not anticipate that it would mean something different in March. So I've been with WhatsApp since 2011. I learned Erlang at WhatsApp, and my focus is mostly on scalability and the multimedia system. I'm honored to work with a fantastic team, but we're small. There's only about 10 of us, plus or minus, that work with Erlang, and we handle all the development and the ops. Now, before I get into why all the things that you need to tweak and change and patch and whatnot to get something of the scale of WhatsApp working on Erlang, I want to start out by saying that it's been a superb choice for WhatsApp, primarily because of scalability in a number of dimensions. Just in terms of programming productivity, I don't think that you'd be hard-pressed to find a better language to be able to support so many users with so few engineers than Erlang. Secondly, just in terms of the scale of systems that you can build using it and the programming model that comes naturally and all the supporting infrastructure with Erlang. And finally, in terms of SMP scalability, it allows us to run very large boxes and keep our node count small. And our operational complexity scales with the number of nodes, not with the number of cores. So the great SMP scalability really gives us an advantage. The other great thing about Erlang is our ability to basically update this thing on the fly, literally on the fly. So we always think about in terms of we're flying an airplane that can never land, but we constantly have to rebuild it to make it bigger. We're constantly adding seats. Gets too heavy, we need to change the engines, we need more fuels, we got to change the wings, and we're doing all this while it's all flying. Now, the question is Erlang our secret sauce? And you could make the argument that it is, but I think an innovation of ours is really what tells a story. We call it founder-directed development, where Jan and Brian personally supervise every line of code as it's written. And it really gives us an advantage in terms of just the quality and what we can produce. So some quick numbers. Most of these you've probably seen in the press if you were following a few of the stories. We've got about 400, we're closing in on 500 million monthly users, 19 billion messages in and 40 billion out per day. You can see the breakdown in terms of pictures, voice messages, and videos. At peak, we have about almost 150 million phones connected to the system at one time. And at peak, phones are connecting and disconnecting at about 230,000 per second. And finally, our peak message rates, you can see coming in about close to 350K and going out just over 700K. In terms of multimedia, the holidays become our biggest throughput time. So on Christmas Eve, we were pushing out at peak about 146 gigabits per second, which when you consider that we're not streaming HD to the home, these are small video files going to phones, is quite a bit of bandwidth. So we had 360 million videos go out on Christmas Eve. About 2 billion photos were downloaded on New Year's Eve at a peak rate of 46,000 a second. And we had one picture that was extremely viral on New Year's Eve that got forwarded 32 million times. So that's kind of the scale of things. Wow, what a revolutionary architecture. So we've got some clients, we've got some front ends that connect that the clients connect to, back-end systems, a little bit of storage to hold on to the messages while they're in transit between the senders and receivers, and that's about it. So I'm going to drill into some of the scale of how those work. Now, when we're sending messages to the phones, some percentage of those are the actual text messages. But we're also sending, at the protocol level, extra messages that include notifications. These are things like group subjects, profile photo changes, things of that nature. And then that red band is our presence messages, so typing, idle, connected, not connected. So when you sum those all up, although the peak message rate out is just over 700K, the total protocol message rate is about 1.6 million a second. On the back end, here's some stats coming out of a couple of our back ends. In the first two lines are from a system which this particular box is hosting 1/4 of the traffic. Now, in the column where you see disk, message in, message out, that's tracking distribution messages. So you can see this one box is taking about 230,000 disk messages a second and going out with about close to 150K out. On the second line, you can see our amnesia stats. That's tracking the number of transactions that are going in and out of amnesia on that particular box. So it's about 11K going in and out. Now, this other box on the bottom here is doing less in terms of distribution. So there's a little less traffic going between nodes. So only about 175,000 messages coming in. But you can see it's doing a lot more amnesia updates. So over in the TM in and TM out columns, it's more like 75,000 writes per second on that particular system. So, we have, I didn't even count them, but we have on the order of maybe a dozen of these types of backends which are running at these kinds of speeds to support the traffic and the things that are going on. In terms of scaling in terms of data storage, so I mentioned that for message, we don't store messages except while they're just in the time between when somebody sends it and the receiver's phone connects and picks it up. For multimedia, it's the same thing. We only store the media during the time that it's in transit, but we need to keep track of what media we have and who it's being sent to. So this is 1/16 of the database for the multimedia. So you can see it's a little over 1 billion records for 1/16. So the total multimedia database is about 18 billion records in amnesia, and that's it's close. Well, there are 200 gigabytes per. So closing in on 2 terabytes of RAM to hold that database. So what's the hardware platform look like to support all this? So we have about 550 servers plus some standby gear. Of those, 150 are the chat servers, which are the ones that handle the messaging traffic that the phones connect directly to. So given that our peak concurrent connection is about 150 million, so that's each one's holding about a million phones. Now, for those of you who've seen my talk from 2 years ago, we were pushing upwards of 2 million connections per server at that point. We're running lower now, basically because A, we run with more headroom because we got a lot more users, and B, well, actually, there's 3 reasons. The second reason is that our users are more active. So we have more users, and they're sending more messages, so the servers get busier. And then we've also moved some functionality that used to be outside those servers into those servers. So they're a lot busier, so we're not getting as many connections per server. There's about 250 of multimedia servers, and our standard config is this dual 2690 V2 Ivy Bridge. They're 10-core packages. So a total of 20 cores, but with hyperthreading, so we've got 40 CPU threads total. And we put between 64 and half a terabyte of RAM, depending on, like the database ones have the large RAM. The standard compute nodes have more like 64 gig in general. We use SSD primarily for reliability, except in the case of video where we need a lot more storage. SSD just becomes a little untenable in terms of cost. In terms of networking, they're all dual link GigE ×2. So we have a front end, which is user facing, and then distribution runs over the back end. So there's dual linked on both of those, both for load balancing and for reliability. And when you add it all up, it's probably a little over 11,000 cores that are running the Erlang system now. As far as software, we're running FreeBSD 9.2 with Erlang R16B01 plus our patch set. That's basically the platform that we're on. Now, when we think about scalability, no surprises here. A lot of decoupling, just stuff that you would expect. Parallelizing stuff as much as we can. We do do as much optimization in the application as we can. Occasionally have to patch OTP or Beam. And then we're always monitoring and measuring how we're doing in terms of capacity and what bottlenecks we might have. So drilling down a little bit into some of the decoupling topics. So the primary thing for us in terms of decoupling is the ability to isolate bottlenecks so that they don't spread through the system. So back-end services that are deeper down in the stack don't bubble up if they have problems out to the front end. And everything's partitioned, and so if one partition has trouble, we don't want the other partitions to be effective. So we can keep as much throughput going as we can while we address whatever issues we might have. Now, if we had a more coupled system, then things are going to cascade pretty quickly at the rates that we run stuff through the system. Now, we try to be as asynchronous as possible. That allows us to keep the throughput as high as possible, even when there are, even when there's latency at various points in the system, or when latency is a little unpredictable. Since we have everything flowing as asynchronously as possible, again, it reduces the amount of coupling and allows us to keep going as fast as we can. So some specific examples of things that we've done. So we avoid transaction coupling in Amnesia. We use Amnesia extensively, but most of the time we're doing it async dirty, without transactions. We use calls only when we're returning data. We need to get something back from a database. Otherwise, we're casting everything all around, again, to preserve that asynchronous mode of operation. When we do need to make calls, we do it using timeouts only, so we don't set monitors. So like a gen server call will typically set a monitor to make sure that the target's there. So we just rely on the timeouts of a cast. Cast that goes nowhere will eventually time out, and so we handle it that way. And that just reduces contention on procs on the far end, and it reduces traffic over the distribution channel. In cases where we only need best effort delivery of something, we'll often use no suspend on the casts. So this allows us to not be affected by downstream problems when either a node starts to have problems or the network between the nodes starts to have problems. In the cases where that happens, eventually the distribution buffers will start to back up on the sending node, and procs that try to send into that node will start getting suspended by the scheduler, and then that just cascades further and further up the system. So in the cases where we don't need to have an assuredness like I said, if we just need best effort to get it there, then we use no suspend, and that way those procs aren't going to get suspended even if there's trouble downstream in what they're trying to get to. And we use large distribution buffers to better absorb those sort of momentary things that we might see on a node, downstream node, or in the distribution network between those nodes. Switching over to parallelizing. So obviously we need to distribute this work over all these 11,000 cores that we have. So if we start with a gen server, a single-threaded approach, we've split that into multiple workers in something we call a gen factory, like a factory floor. There's a dispatch process that spreads the work. But it turns out that once we got to a certain point, the dispatch process itself became a bottleneck, and not necessarily just because of the execute time, but as we have a lot of nodes coming in to a particular box and there's a dispatch process, the locks on that process become a bottleneck between the distribution ports that are coming in and the process itself. So by spreading that dispatch out across, so we have a gen industry, which is a layer above gen factory. We have multiple dispatch procs, and so that allows us to parallelize all the input coming into the box, as well as doing the dispatch down to the workers themselves. Now, the workers are selected via a key for most of the sort of the database type of operations. But in the cases where we have a non-deterministic latency, we use a FIFO model for distributing that stuff so that we don't get head-of-line blocking. Now, as you'd expect, all our services are partitioned. We usually, at this point, are partitioning between 2 and 32 ways. Most stuff is 32 right now. We use PG2 addressing to address those partitions throughout the cluster. And usually what we do is we run them in pairs. So a particular node will be primary for one partition and secondary for another, and then they'll have a peer, which is the flip. And if one or the other of them goes down, then they'll be handling both primary traffic and secondary traffic. As far as parallelizing what happens with Amnesia, like I mentioned, we're doing mostly async dirty. And to give us as much consistency as possible, since we don't have transactions running around this stuff, we isolate all the record access to a single process on a single node via hashing. So we're hashing to a partition, which is hashing to an Amnesia fragment. It's going to actually end up being dispatched down to one factory, one worker, and so all the access on a single record is going through a single process. We also ensure that each Amnesia fragment is only being written to or read from on one node at the application level, and that allows us to have replication streams that only go in one direction. So if we have two peers, one side's doing access to one set of fragments and replicating to the other side, and the other, its peer node, is doing the same in the reverse versa direction, but they're not sharing application access on the same fragments at the same time. Now, at the rate that we're doing writes on Amnesia, even doing it async dirty, we have a bottleneck in terms of how much we can push through a replication channel. So, actually, I'm jumping ahead. This is a different one. Same issue, though. If there's a replication stream going between peers, the Amnesia TM becomes a bottleneck in terms of how fast it can update the fragments. So we patched OTP to have multiple Amnesia TMs running for async dirty only. There's still a master Amnesia TM that's running for the transactional stuff, but for async dirty applying records, it all happens in parallel. So that gave us a lot more throughput in terms of replication. Another patch we applied was to allow the Amnesia library directory to be split over multiple directories, which allows it to put on multiple drives and get increased throughput to the disks, especially obviously when they're dumping. And it's a real issue during load time. When Amnesia's loading from the peer, it's load, and then it's a whole bunch of dumping. And being able to spread that I/O over multiple drives, even SSD, gives us a lot more scalability in terms of how fast we can load our databases. Finally, we've been shrinking our Amnesia islands more and more. At this point, we're basically running 2 nodes per island. So an island is basically the Amnesia cluster. So even if we've got, say, 32 partitions, we'd only have 16. We'd have 16 separate islands that support that particular table. So that in this, we do this for 2 reasons. It gives us better opportunity to complete schema operations under load, because there's only 2 nodes that have to get into a state where they can complete the schema operation. And it also reduces the amount of load time coordination if we're trying to bring either one node or both nodes up at the same time. There's not as many nodes in the Amnesia cluster that need to coordinate that load. Moving back to some more decoupling. So I mentioned head-of-line blocking. We separate read and write queues in places, especially where we're doing transactions on the tables, so that if there's any latency issues on the write side, that doesn't block the read side, because in general the read side is going much faster. So if there's any backup, we can quickly get a queue that's out of control if we don't split those. Another thing that we ran into early on was, again, if a node runs into trouble or a network between a particular node and another set of nodes runs into trouble, that distribution channel backs up. You start getting disk-port busies, and that backs up all the way into the application that's doing the casts, and even if they're casting to multiple nodes. So what we do is so when we're doing stuff internode, we hand that off into separate procs, so that if there is a problem with a particular node, only the messages that are destined for that node are going to get backed up, which they have to anyway because it's not working right. But messages that are going to other nodes can flow freely without interruption. So it keeps the throughput up and isolates the problem to exactly where it is. So we use that for when we're doing node-to-node message forwarding, especially on those front ends, and then also made a patch to Amnesia to do that at the async dirty replication time. So ordinarily, when you do an async dirty write with replication, the local process does a write into the ETS table on the local node and then does the cast to the remote node. So what we do is we hand that cast off to a set of workers that are specific to that node, so that the replication streams are both running in parallel. So we've got multiple replication streams outbound to each node, and there's separate ones per node. So if a single node has a trouble or the network has trouble, then again the replication stream for it stops, but that back pressure doesn't go all the way up into the application that's doing the original write. Again, we're trying to decouple this as much as possible so that if there's issues, they get isolated into just the places that actually, there's nothing we can do about it, but that everything else keeps flowing. And then I mentioned when we're doing things with non-deterministic latency, we'll use the queuer model or a FIFO worker dispatch so that we don't get head-of-line blocking on those types of operations. So here's an example of some optimizing work we did. The offline storage system used to be a big bottleneck when we had load spikes because we just couldn't push stuff to the file system fast enough. Now, it turns out that most messages are picked up very quickly. I think the last time I looked, it's something like 50% within 60 seconds. So in a lot of cases, we'd like to be able to deliver those messages before we even have to push them into the file system. So we added a write-back cache with a variable sync delay, how long it would sit in the cache before it actually gets pushed into the file system. And what that allowed us to do is, for a lot of messages, they get served directly out of the cache without ever touching the file system. And in cases where the I/O system falls behind, we get a large load excursion. That sync delay can basically absorb. It gives us extra. The write-back cache gives us extra buffering, so that we can continue to deliver messages at full rate while the I/O system tries to catch up. So you can see here some statistics. I don't know if it's readable back there, but basically under normal conditions, that one right in the middle, XCAC, that's the percentage of messages which are the percentage of pops. A pop is when a phone connects, we pop their mailbox and deliver all their messages. So the percentage of pops that can be handled exclusively out of the cache, it's 98.7%, so extremely high percentage. Just to the right, the sync age, so we usually run with about a 20-second sync age. That's the delay between when it gets put in the cache and when it gets flushed to the file system. And then the max age, the next one, 51,000 seconds. So the better part of a day of messages, or the oldest message in the cache at that point is the better part of a day old. So that one's been long since flushed to disk, but it's in the cache, so we don't actually have to touch the disk to pull it back out. Some recent improvements to offline. We fixed a head-of-line blocking problem in async file I/O. So Beam wants to hash the file port and assign all the I/O for a file port to a single async thread, which for us was a problem because the way the offline system works is each cache partition, and there's 48 cache partitions per node, each one only has one file port that it's doing all its I/O over. So we'd have a situation where a large mailbox or a slow disk or whatever would slow down a particular async thread, and then everything on that cache partition would get blocked behind it. So I patched Beam so that we could round robin our file port requests to all the async worker threads, and that smoothed everything out. And I'm not quite sure why it hashes that way, because all the file I/O is synchronous at that level, but I'm sure there's a good reason. But for us, this was a big win in terms of keeping that offline system performant in the face of some varying sizes and latencies on the I/O. And finally, we got better at handling large mailboxes. We found that that very large mailboxes, people who either are in a tremendous amount of groups and are getting thousands of messages per hour, were polluting the cache and really slowing things down. So by evicting and keeping large mailboxes out of the cache, it greatly enhanced their improvement, or enhanced the performance of that system. Okay, another example. This was a fun one. Our account table has 512 fragments, amnesia fragments, and we're partitioning this into those islands, and which means that there's basically a sparse mapping of the users over these 512 fragments. So any given partition is going to be only accessing a small percentage of the fragments, and all the rest are going to be empty and idle. So we doubled the number of hosts because we were running close to capacity on that system, and the throughput actually went down. And after a little bit of digging, we discovered that the record access was at the ETS level was really slow. So I took a look at ETS info stats on a few of the amnesia ETS fragments, and discovered that the hash chains the maximum hash chain size was being reported at over 2,000. The target for ETS is like 6 or 7, so this was a problem. So what was happening is ETS basically uses phash2 as its mechanism for hashing over its linear hash, and we were using phash2 at the higher level to select partitions. So since the hashes were coincident, we had a large number of empty buckets in the ETS hash linear hash, and a few that were extremely long. And ETS uses the average chain length to decide when to split the hash. So the average was 7, even though the maximum was huge. So this two-line change to basically seed the hash so that phash2 and the ETS hash didn't coincide basically eliminated that so that we get the full width of the linear hash in ETS. And that two-line change, this was one of those really exciting days where we deployed this, and it gave us like a 4-to-1 improvement of speed on that particular box. Now, as far as patching, so we're not patching FreeBSD anymore, and the configuration changes are pretty minor, just things that you'd expect for a large network stack and large RAM. I'm not going to go through the patches that were still running from my talk 2 years ago that we've been ported forward to R16, but I've described those in the other talk. Some of the new ones since then, we did run into problems with contention on the timer wheels. It was sort of like the last big chunk of contention that lock counting showed in Beam. And it's easy to understand because if we have 1 million or 2 million connections into a single host, and each of those is setting and resetting a timer every time something happens with that particular phone, we're talking about hundreds of thousands of timer sets and resets per second. So with having just one timer wheel and one lock, that was a big source of contention. So I split that into multiple timer wheels. There's basically one per scheduler. I mean, they're not tied to a scheduler, but that it's on the same order. And that basically eliminated that contention and gave us pretty clean stats on lock contention using lock counting. A couple problems with, there's a problem with Amnesia TM in that it's a big select receive loop. So under load, trying to load tables created a problem because we'd get backlog in the Amnesia TM as it's loading, and it would get to a point of no return because of the selective receive. So there was a little patch to pull stuff out of the incoming transaction stream and save it to process later so that the selective receive would run quickly. I mentioned before that we added the multiple async dirty senders. I added mark and set on a port because prim file has a selective receive. So when you're doing file I/O, when Amnesia was trying to dump a table, it's doing file I/O. In the context of that same process, if it's taking a lot of message input, this would be in the transaction manager again. That would get into a point of no return amount of backlog because of that selective receive. So adding the ability to do a mark and set on that file port allowed that selective receive to be taken out of the equation, and so that we could go run full speed dumping those tables. And then finally, some of our clusters span the continent, and so I taught Amnesia how to load from a nearby node rather than pulling stuff cross country. I mentioned the round-robin scheduling for async file I/O and breaking the hash coincidence. Made a pass on optimizing the ETS main and name tables, which are accessed on every ETS operation. So on those nodes where we have lots of fragments, several tables with lots of fragments, it's lots of ETS tables. There was a lot of contention on those tables. And then finally, we were running with a patch so that if Amnesia is already dumping a table and another dump gets triggered, that it doesn't queue that up. Because we get in a situation where there were so many where we'd fall behind on dumping, and there would be so many dumps queued up that would never complete, and you can't complete a schema operation in Amnesia while there's a dump pending. So we get in this situation where we couldn't do schema ops while the system was running because all these queued up dumps. And there's really no point in queuing the extra dumps because it's dumping as fast as it can. All right, a little more about decoupling. You see the size of our cluster, and it's getting a little bit large. I mean, we're not running into too many problems, but we needed a way to be able to contain the size of the cluster and also allow it to span long distances. So I built this dist-like transport over GenTCP, which basically runs like dist, only instead of connecting all nodes, the mesh is just between the nodes that need to talk to each other. And we use a transparent routing layer just above PG2 to determine whether, if we have a lookup for a particular PG2 group, we look in the local PG2, is it on the current cluster, or it can look at each of the other WAN disk connections it has, and it says, oh, I see this group on this WAN disk connection, and it can forward it across. And it's all just single hop routing. There's no multiple hops to get through this thing. It looks like this. So we've got 2 main clusters in 2 different data centers, 2 multimedia clusters in 2 different data centers, and then we might have a shared set of global clusters between the 2, and they all have WAN disk connections between them. Drilling down, they'd look like this, where the mesh is just between the nodes that need to talk to each other, but it's not a fully connected mesh. And again, this is what the routing looks like. So any given client will have a list of WANDIS links with the PG2 groups that have been published from the far end onto those groups, and so they can make their local routing decisions. And I apologize, I'm going fast. I need to run out of here to catch a flight, so I'm trying to leave lots of time for questions. All right, so scalability for us is kind of like clearing a minefield, and we're generally able to detect them and diffuse them before they explode, because we get lots of world events, especially live sports, creates big vertical load spikes when, say, goals happen or the game's over. We get server failures. It's usually RAM. We have network problems, and hypothetically, we could have bad software pushes. I mean, it never happens at WhatsApp, but now we're not always successful. You may have read about an outage on the 22nd, which, although it was severe, at least the timing was almost as bad as it could possibly be. So contrary to popular belief, it had nothing to do with load. It started with a backend router glitch. We actually had a short incident the night before where that same backend router dropped OSPF, but it didn't affect us very much. In the morning, however, it dropped our VLAN, which caused a massive node disconnect and reconnect throughout the cluster. And when everything reconnected, it was in this unstable state that we had never, ever seen before. We tried unsuccessfully to stabilize it, and we finally decided that we had to stop everything. So that plane that never lands had to land. So this is the first time we had ever had to do this in years, and it was a time-consuming process to bring everything down, start it all back up, and get it running. And it was, in the process of doing that, we found one overly coupled subsystem. It was just a side effect. It wasn't the cause. But it turns out that we believe what happened was with that mass disconnect reconnect, PG2 actually can get into a state where it's doing n-cubed messaging. Because what we were seeing was basically PG2 message queues going from like 0 to 4 million within seconds. So we're rolling out a patch to try to cut down on that messaging, so that if we ever see that sort of disconnect reconnect again, that it won't get into that state. And I'm just going to stop here and hopefully leave a lot of time for questions. How do we deal with network partitions in Amnesia? So we alert on it quickly, and then basically we have a reconciliation. I mean, we continue running, even though the nodes are now they've disconnected at the Amnesia level. So we continue running, and then we have a reconciliation process, which is mostly manual now, where we dump one side and reconcile on the other side, and do the vice versa to basically recombine them. And we join them back. Well, we join them back together immediately, and then we go back through and reconcile the tables, basically by a dump and load. Yeah.
So the island that you mentioned, so that's an Amnesia cluster of 2 nodes only. So
right.
Replication is only happening on 2 nodes.
Right. Exactly. Yeah. So even if so the question is the islands of 2. So even if we've got, say, 16 partitions. Each of those partitions will be its own little Amnesia cluster of only 2 nodes, so that there's only replication flowing between 2 peers and only in one direction. Yeah?
Do you experience any scalability issues with ETS?
Scalability issues with ETS. Not that you wouldn't expect. I mean, we generally partition things enough so that we don't have a lot of concurrent access from a lot of procs. So we generally try to limit the number of procs that might simultaneously access a single ETS table or a single Amnesia fragment, usually, to about 8. So as long as we keep the potential number of workers that might access a given fragment down to about 8, then that keeps the contention, the lock contention, pretty much under control, and so we can. It doesn't become the primary bottleneck on that particular case. But of course, I mean, it's locking, right? So we're always looking for ways to improve that. I actually ran an experiment with, because Amnesia, unless it's changed recently, last time I looked, didn't have a way to turn on read and write concurrency on ETS. So I experimented with running with a patched Amnesia on one of our high volume tables to turn those on, and I actually wasn't able to see a difference, but it was just a quick test. So I think we need to do some more analysis on how that was, why that was, because it was unexpected. I expected it to be a lot better, and it wasn't. Yeah.
So how do you actually simulate some of the loads that you have in order to do things like what you just suggested?
Yeah, well, even 2 years ago, I was saying, the question is, how do we simulate this load? And the answer is we don't, because it's extremely difficult. I mean, even 2 years ago, when our traffic was 1/10 what it is now, it was just so difficult to simulate the load that we do. So if we have something extremely disruptive that we're trying out, we roll it out very slowly. We'll put it on something that isn't taking, that's not only a small piece of the traffic, but isn't taking all of that traffic, and just quickly iterate on that until we're confident that it's working well, and then roll it out across the rest of the cluster. Because otherwise, it's so difficult at this scale to simulate what's actually going to happen, especially in these weird cases, in cases where there's huge excursions. It's New Year's Eve at midnight or those types of things. Yeah, in the back. How do we roll them out? Well, basically we create. We just have a set of versions that we're just rolling forward. So we call them WA. So we're on like WA42 now, which is basically all of the OTP package built with our patch set, and then we just we do rolling upgrades. So everything's redundant. So in the case that we want to do a beam upgrade across a subsystem or whatever it is, we'll install it and then gradually do restarts across that cluster to pick up the new changes. In a rare circumstance, if it's just an Erlang patch that we can hot load, something in the OTP libraries as opposed to Beam, then we'll roll it out without a complete restart. But that's rare. We usually just upgrade the whole thing. More questions? Yeah.
One follow-up question to the island question.
Mm-hmm.
So you said it was one way. The replication was one way.
Right.
How could you do that?
Well, it's one way because we ensure. Okay, so the question is, why is replication only one way in our Amnesia islands? It's because we ensure that the traffic is only steered one direction or the other. So, in the case of a set of fragments, so let's say we had a two-fragment table in an island of two, we'd make sure that all the one traffic goes to one node and all the two traffic goes to the other node. So one node will only see application access for one of its fragments, and it'll replicate the other direction. On the other node, all it's seeing on the fragments that it's secondary for, that it's not primary for, the only traffic it sees is replication traffic. So the other reason the primary reason we do that is, first of all, it's better for operational simplicity, but also it reduces the amount of contention. So instead of having both the application access and the transaction manager applying updates, competing for the same locks on those ETS tables, it's either one or the other. So it reduces the amount of contention on those replication streams. How are we doing on time? We still got more time. So I can talk more if because I blew through some stuff, yeah. Oh, challenges, yeah. Why don't I do that? And then I'll answer your question, Anthony. Remaining challenges. Okay, so DB scaling, especially our multimedia database, is a issue. Now, as I mentioned, I'm not sure, but some of you may have tables that are as big as 18 billion records. But it gets a little unwieldy, especially trying to load. So we had direct experience with this 2 weeks ago. But I mean, these databases actually get reloaded on a fairly regular basis as we do upgrades, and we're limited by how much we can push in at a time. So those databases can load at about 1 million records a second, But the real problem is that sometimes the load will fail because right when it gets to the end of loading, if you're, I don't know if you're familiar with the way an amnesia table loads, but it basically finds another node on the network that has the table fragment that it wants to load and sets up a load stream from that fragment. So it loads, all goes into memory. Once it's into memory on the load that's loading, the node that's loading, then it dumps it to disk. And the problem is when we start, we don't want to do one loader at a time, so we run multiple loaders at a time. We try to run with 16 loaders simultaneously. Sometimes that works, sometimes it doesn't. Sometimes we have to back it off to like 8 loaders. But the problem is since all these tables are partitioned pretty accurately, they're all the same size, so they all finish loading at the same time and they all start dumping at the same time. So on this multimedia database, it'll load at 1 million records a second. After 15 minutes, it goes to dump, and well, it's loading multiple fragments during there, but they all tend to line up, and so we had to add that parallel disk I/O because Amnesia would like to dump. As this system's loading, it can push over. I have it on there, over 700 megabytes a second to the disk. But even that's not enough because at the point that it's dumping, it turns on the replication stream. So the replication stream's coming on, and I don't completely understand what the state is, but it's the table's kind of blocked, but it's also accepting the replication stream. So we start generating backlog, and if the dump finishes in time before the backlog gets to a point of no return, we're okay. But occasionally, they'll line up in such a way that backlog just becomes unrecoverable, and the node ends up just blowing up and crashing, and we have to restart the load. So I patched one selective receive issue there, but I think there are a couple more that need to be fixed so that we get reliable starts on these big databases. The cluster is becoming big enough that sort of real-time cluster status and control at scale is an issue for us. And I don't mean in terms of sort of the typical operation. I mean, the reason there are plenty of cool operational tools out there, even some that are Erlang based. People over here, but there's kind of a specific set of things we need to look at when we're diagnosing problems, and a specific set of actions that we need to take. And in the past, just having a bunch of shell windows was enough. But now that we have, say, 150 front ends for chat and 250 for MMS, that you can't really get 250 windows on a screen. So we're going to have to figure out a better solution to that. And then finally, Power 2 partitioning is going to be an issue before too long. I mean, we're at 32 partitions now. Next one's 64. That's not too bad. When we start jumping in increments of 64 and 128 and 256, then that at a certain point we're going to have to say, okay, we need something better than that. For now it's okay, but we're maybe 1 or 2 steps away from where it's going to be kind of impractical to take the next step without doing something more intelligent. Let me answer Anthony's first. Yeah.
I was just curious about your Gen factory and Gen industry.
Uh-huh.
Plans to sort of open source those?
I think so. I think you know. Eugene, you asked me that a couple weeks ago. We'll think about it, yeah.
How big is your screen so it fits 256?
No, I think the most, actually, usually I run, so I have a, I don't know, 30-inch monitor. So usually I run out of pitties before I run out of screen real estate, but yeah. Yeah.
Given your monthly active users, you don't have that many hours of queues to go before you run out of users.
Well, that's true. Good point. Thank you. You solved the problem. Yeah.
What was the most entertaining part of the whole project to build?
Most entertaining part of the project to build? Entertaining.
Good or bad?
That's a good question. Well, yeah. I mean, the thing that's really exciting for us, I mean, the number that I'm proud, I showed you all those numbers. The number I'm proudest of is number of users to number of engineers. I mean, because like 40 million users per engineer. That's I'm really proud of the way we've been able to scale the system with a small team and be able to operate the whole thing. That's not really a source of entertainment, it's a source of pride, but entertaining part of the system, gosh. Well, I think, so I rebuilt the multimedia system 2 years ago, and what was exciting about that was that we made it we reduced a lot of friction in being able to send pictures and send video, and then eventually we added the voice messages, the easy push-to-talk voice messages last year. And seeing how users responded to that was really satisfying. They're like, "Wow, this is easy," and then we watch our bandwidth bill go like, "Woo!" But just being able to see how people wanted to connect in ways other than just text messages was really satisfying. How are we doing on time? Yeah.
You talk about the rest. You have 10 Erlang engineers.
Right.
And how about the rest of the tech team?
It's mostly most of the rest of the tech team are work on our clients. So since we strive to support every smartphone platform there is, we've got teams of several engineers on each platform. So the bulk of those are working on that. We have a couple engineers that are working on our upcoming voice over IP stuff. We're all contributing to that, but a few that are dedicated to that, and that's basically it. Like I said, the Erlang team handles all the operations of the cluster basically, and there really isn't anybody else technical. And the rest of the WhatsApp team are our customer support people, and a few G&A folks. Anything else?
So your Erlang team also handles the network ops?
Well, we run on the cloud, so yeah. It's not quite fair to say that we're 40 million users per engineer because there's a large team underneath us running the infrastructure in terms of networking and the data center and that, which isn't counted in the 55 people at WhatsApp. We interface with them in terms of problems that we're having, especially when things like that outage happen. But we don't do any direct stuff on the network side or the server side. I thought, let's see, I have time for a couple more questions.
What is your cloud provider?
I'm sorry?
What is your cloud provider?
I don't know if I can say that. Well, that's true. You can do Richie Nest. It's SoftLayer. We have a great relationship with them. We get these very large boxes, bare metal. We do all the, we install the OS, we install the application, we do all that. They take care of the hardware and the network, and it's worked out really well for us. There's still a certain amount of shared tenancy going on with the network, but for the most part, we're running isolated. Yeah.
Have you had any significant problems with distributed system issues? Have you had like split brain problems with amnesia or any kind of?
Well, I answered. As I mentioned the other guy, occasionally, it doesn't happen a lot. We get a really reliable network on the back end, which we like. But there are occasions where the nodes will run into problems. But occasionally, like there will be network problems, and we'll get node disconnects, amnesia inconsistent. They'll run split. We'll join them back together and do that reconciliation process. But other than that, and the 22nd where the whole thing disconnected and it created a huge distributed system problem, it's been super reliable. Even at the scale of the cluster that we're running, which is 450 nodes or something like that. Yeah. All right, I got to run and catch a flight, but thank you for your attention.